this, see what I can do to catch us up. So first of all, I'm going to do an example. So my goal here is to describe solution sets. Or let's say the solution of AX equals to B in view of subspace dimension and so forth. So that's my goal in our discussion here, is to explain yet again how do you solve AX equal to B for A in a binomial matrix, B a given, inhomogeneous term. And so to do that, actually, we have to talk about the null space of A. All right, it's all about the null space actually. So we've talked about null space. We proved that null space was a subspace before, right? But what I haven't done yet is really just hone in on the issue of how do you calculate a basis for the null space. So let's go ahead and take a minute or two, 3, or however many it takes, to look at an example. So let's suppose A is equal to GIO. Let's make it up 1, 2, 3, 4. 1, 1, 1, 1. And then 3, 3, 4, 5. This may possibly be interesting. Let's calculate the null space of A. All right, so kind of takes us back to first week, right? We're actually going to have to do a calculation. Row reduction, right? So I'm going to do it. Let's see here. So row 2 minus row 1, and row 3 minus 3 row 1. What do I get? 1, 2, 3, 4 upstairs. 0. Minus 1. Minus 2. Minus 3. 0. Minus 3.
Minus 5.
Minus 7. Minus 3, minus 5, minus 7.
No, it's not. Okay, so 3 times 3 is 9. 9
I thought I heard a minus 5 and minus 7.
It's minus 5.
I think I heard a pi.
It's pony.
So,
It equals 9. 9 minus 5 equals 9.
sorry, I looked away from the board. What was this? So we agreed that this is
Minus 5.
Minus 5. Minus 5, okay.
9 minus 11.
Minus 11? So,
No, minus 7, you're right.
It's pi squared.
Whatever. You guys wanted minus 7 to be the other one, though, so you were both wrong. Whatever.
We put ghost there.
all right. Moving on.
Change 8 goes.
Moving on. Let's see here. So what can we do next?
Row 1 plus
Row
2
2 times negative 1.
row 2.
I think I'm going to pick on row 3, right? Row 3. Row 3. We say row 3 minus 3 row 2. I think maybe somebody said. Is that right?
Yeah, and then we do row 1 plus 2 row 2. If you want to do it at some time.
Row 1 plus 2 row 2?
Yeah.
I'll do that too. Sure, why not? Row 1 plus 2 row 2.
And we could probably do row 2
Oh,
times
that's it, that's it. You get to read now. 1, 0, plus 2 row 2, right? So that's what? Minus 1? 2? Minus 2, right? So I'm adding twice row 2 to row 1. Yeah. And then we're not doing anything to row 2, it's just, you're probably telling me I could multiply that by minus 1, right?
Yeah.
Yes.
That's what I said.
And yes, I'm ignoring you guys. Sorry. So 0, 0. Yeah, it's more writing for you. That's true. I guess I have what's coming to me. Row 3 minus 3 row 2, which is what? 1. All right. And then what? 2. All right. All right. And now we can clear out this guy. So I have row 1 plus row 3. And row 2 plus 2 row 3, what do I get to? 1, 0, 0, 0. Yeah, okay. 0, minus 1, 0, 1, right? 0, 0, 1, 2. And then finally, minus row 2. Here is a stupid notation. Hey. Anyway, my point to you is that this is the reduced row echelon form of A, right? Okay. So, let's see. What can we say? What's the basis for the column space of A? Well, what is the column space of A? Column space of A is the span of what? I mean, you could look at it as 1, 1, 3, 2, 1, 3, and 3, 1, 4, right? That seems like a lot of writing because we could just look at this and go, aha, column space is a what? It's a subset of three-dimensional space. I have 3 linearly independent columns in the reduction, therefore by the column correspondence property, the original 3 columns were also linearly independent. 3 linearly independent vectors, it has to span everything. So column space of A is in fact R3.
So why don't you add that for
What's that?
Why don't you add that for or not column?
I mean, I don't need to. Yeah.
So because of that, we learned like first part of this class, it works the same way. So you could either use E1, E2, E3, or you could use those first 2 columns of A because the full column corresponds to the span.
Yeah, and be careful. Suppose that this had worked out different, all right? And suppose that the last row ended up being zeros all the way across. It would not be true that I could use E1 and E2 to get the span of the column space.
You have to get the reduced row echelon form first.
No. This is false. You have to use the columns of the original matrix. For example, Landon, a really, really simple example that's easy to see. Take A just to be a column vector. Say 1, 2, 3, 4. All right? What's the reduced row echelon form of A? 1, 2, right? Notice that the span of 1, 2, 3, 4, stupid set notation, is not the span. So it's not, you don't use the columns of the reduced row echelon form to form the basis for the column space. You actually have to use the original columns. That is, of course, but you're not wrong in this example because it's the whole space. So E1, E2, E3 is another basis for R3. So in that case, it gets you the same span. But that's a happy accident. It is true, however, that you could use, it's hard to see in this example, but you can use the rows. You can use the rows of the reduced one for a basis for the row space of A. That is true. Yeah.
You have to have the first column or span. Like the thing is like the first column doesn't seem to actually like coincide with like the.
I absolutely need the first column here, yeah, because I can't build this first column from any of the remaining 3. Now I could trade column 3 for either column 1, 2, or column 3. I mean, I could take a column 4 in place of one of these guys because I can build this from either this and that or this and that.
Okay.
I mean, choose 2 of these where at least one of them is, well, I don't know. I think any 2 of those work. Is that true? Any choice of the last, any 2 of the last? Anyway, this is somewhat beside the point. The point is not what are all possible bases. The question is, more specifically, what is a basis for column space? Here it is. Actually, even that is somewhat beside the point. I'm just reminding you guys. Getting back on track here. We want to find description for AX equals to B, all right? So this is column space. How about null space? What's the null space look like here? Remember what null space was?
It's all x such that ax equals 0.
Right, x such that ax equals to 0. This is a subset of what? I mean, actually, it's a subspace. We proved that the other day. Subspace of what? Not R3,
R4.
R4. Very true. So, because I have a 3 by 4, I have to multiply by 4 by 1 to make that matrix, for those to be an allowed multiplication for it to make sense. So, what is the null space of A? I mean, okay, there it is, but what's the basis for it? Let me erase that. Everybody have this comment? Actually, it's interesting you make that comment then, because that is one of the canonical and most favored mistakes on the next test, using the columns from the reduced or echelon form as opposed to the matrix to form the column space. It's a very popular mistake.
Keep in mind, so that makes points.
I hope I'm not, through this discussion, inadvertently making it come up and with a vengeance again. I never know if I'm hurting or helping with these kinds of comments. Okay, so the null space of A is what? It's like, okay, x in our case R4 such that ax equals 0. But that's the same as, I mean, let's let x equal to x1, x2, x3, x4, for lack of a better idea. And because that's what we usually do. Well, you can read from the reduced to echelon form what? You know that ref of A concatenated with 0 is equal to what? It's equal to 1, 0, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 0, 1, 2, 0. Because if you do a row reduction with an extra column of zeros, just 0 plus 0 plus 0 plus 0, all the steps don't change it, right? We talked about this before. So I can see what the solution should be to the equation ax equal to 0 from this, right? What's the solution? x1 equals to what? 0. Now, x2 equals to what?
x4.
Yeah, x2 equals to x4. Notice that the minus becomes a plus when it moves to the other side. And then x3 equals to what?
2 minus 2x4.
Yeah, minus 2x4. Now, of course, we usually like to write the solution set. What's the solution set look like?
X4 is 0, x4, 2x4, or negative 2x4, and then x4.
Okay, 0, x4, minus 2x4, x4 again, right? Yeah.
Sorry for being so.
Sorry?
Such that x4 belongs first.
Sorry. Christian seems sad today. I shouldn't pick on him.
I mean,
And I'm not literally, not metaphorically. That's a great fan. Sorry, it's in my nature to pick on you. I can't say something and not accidentally somehow criticize you.
I need hazard pay.
It's
I
like
need credit.
It's like part of my very being. Of course, the solution set is exactly the null space, isn't it? Yes.
Does x bar be an element of R4 or just R?
Does x?
X4? Like how you have.
X4 is a real.
It's just a number.
Just a number. Yeah. Oh yes, that's not a typo. I do mean R. X, on the other hand, is an element of R4. X is a vector. X4 is a component. A scalar variable, if you like. Let's do some counting. Now, I guess this example isn't the greatest for seeing how the null space is formed. I'll give you another one here in just a second. But let's just take a second to smell the roses here.
The letters smell terrible.
They're there. Let's see here.
The roses. Sorry.
Okay, so here's the definition for you. The rank of A is equal to the dimension of the column space of A. All right, the nullity of A is equal to the dimension of the null space of A. Since writing nullity and rank out is kind of a drag, we at times will use the following abbreviations: RKA for rank, or Greek as new. So rank and nullity are specific numbers which describe a given matrix.
What's the symbol for the nullity? What
New.
is it?
Okay.
New. Yeah.
Is it actually like NEW?
Is that new to you?
Or is it U?
Sorry.
That's a weird thing.
It's a Greek letter.
I feel like when
Okay, so what's the significance of rank and nullity here? I mean, if you look at the, we have what? The rank, for this example, what do we got? We got rank of A is 3. And we had the nullity of A was what? What's the dimension of the null space?
4.
No.
Like, oh, what?
How many vectors does it take to get a linearly independent spanning set for the null space?
1.
Just one.
That's, okay.
1 plus 3
Oh, yeah, yeah.
equals 4. What is the significance of 4 for this example?
It's in our book on number of columns.
Right. It's the number of columns in the matrix.
Universal matrix.
Right, in A. So this is the rank nullity theorem. If A is an element of Rm by n, then the rank of A plus the nullity of A is equal to n. So let me show you another example of this. I don't want to actually work out another row reduction because they're kind of a drag. But let's suppose that A is like, gee, I don't know, 4 by 6. All right, and suppose the reduced for echelon form of A is equal to the following. So let's say 1, 0, 0, 0. I'm doing the first column, and then 2, doing the second column, third column, 0, 1, 0, 0, fourth column, minus 1, 3, 0, 0. Fifth column, 1, 1. Sixth column, minus 2, minus 3, 0, 0. Okay, this is probably an awful example, but there it is. Suppose you have a 4 by 6 matrix and that's its row reduction. What's the rank and what's the nullity? So I want us to find the rank of A, the nullity of A, and a basis for the null space of A.
So in order to find the rank or the nullity, all you have to do is like find one and then just subtract from the columns and find the other one. So you would just do the easiest already method, right?
Well, the rank is the dimension of the column space, right? So the rank of A would be what? Rank of A is the dimension of the column space of A, which is equal to the number of linear independent columns.
2, right?
Yeah, which is equal to 2 here because there are 2 pivot columns.
That means there are nullity is 4.
That's right. It means the nullity is 4. What's the significance of the nullity as you think about the null space? Like, the nullity is the number of parameters that you need to form the span, basically. So for this one, I have what? I've got like x1 equals to what? x1 minus 2x2, right? Plus x4. 1, 2, need a number here. 1, 2, 3, 4, 5, 6 to be straight. Minus 2x2 plus x4 minus x5 plus 2x6
Just write on
x3. What happened?
and like just write on this little bar. It won't tell me.
Oh, let's see here. Minus 3x4 minus x5 plus 3x6, all right? So x in the null space of A tells me that x is equal to, you just write it out. So I got minus 2 x2 plus x4 minus x5 plus 2x6 comma x2 comma minus 3x4 minus x5 plus 3x6 comma, where am I? 1, 2, 3, 4, 5, 6. Very easily makes some YouTube. Let's see here. And then, so what's, define the actual basis for the null space, right? You just factor, you pull out the variables right here that correspond to the non-pivot columns, which in this case is everything except for 1 and 3, right? And you'll be able to write this as a linear combination of certain vectors. What are those vectors? I mean, x2 times what? You got yourself a minus 2, comma 1, comma 0, 0, 0, 0. Plus x4 times what? x4 times, got yourself a 1, 0, minus 3, 1, 0, 0. Plus, what's the next one? x5. You got yourself a minus 1 in the first slot. There's no x5 in the second slot. In the third slot, you got minus 1 x5. Fourth slot, no x5. Fifth slot, there's an x5, so that's 1. Sixth slot, no x5, so 0. And then x6. Let's see, first slot, I got 2 of them. Second slot, none of them. Third slot, 3. Fourth slot, there's x4, there's no x6 there, that's 0. x5 is 0, x6 is, x6 is 1, x6. These vectors have to be linearly independent. Why?
Like the vectors you just wrote, right?
Yeah, why do these vectors that I factored out, why must they be linearly independent? I'll put it into words for you. If they were linearly dependent, that would mean that the parameters are redundant. That would mean that you could class 2 of the parameters into like 1 parameter, which would mean that there's some other like linear dependence between the columns, which wasn't already there, so you could like eliminate one. I mean, it's tied to the fact that, these are independent columns. I don't know if I've said it right or not, but it is in fact always the case that these have to be linearly independent when you do this calculation. Yeah.
So if they were linearly dependent, that means that wouldn't be the reduced row echelon form of A.
That's true, although I need to interpret that in the right way, yes. Yes, Christian?
And basically, those are like the rows that you made. Wait, no, not the rows.
These are columns. These are R5. They're not in the matrix, is the thing.
Oh, okay, I thought you were.
They're not, the basis for the null space is not seen in the original matrix itself. The basis for the column space is very different. Basis for the column space actually is found in the matrix itself. However, basis for the null space is somewhat intangible. You actually have to do a little calculation to see it. You can't see it in the matrix itself.
I was getting really excited. I thought you were actually going to like find matrix A from an RRA.
I know there's actually infinitely many A which fit the bill here. I mean, it's okay. But the null space is minus 2, 1, 0, 0, 0, 0, comma, dot, 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 comma. Sorry, I'm not writing them all out. 2, 0. I think you get the idea, I hope. 0, 0, 1, I mean.
So we just find
There's
one of this.
4 linearly independent vectors here, right? The nullity of A is equal to 4. What's the proof of the rank nullity theorem? How do you prove it? It's essentially from the reduced row echelon form of the matrix, okay? I mean, that's one way to prove it at least. To prove that the rank plus the nullity is the number of columns, just think about the reduced row echelon form. In the reduced row echelon form of the matrix, you either have pivot columns or non-pivot columns. To each pivot column, you get a contribution to the rank. To each non-pivot column, it contributes one dependent variable to the null space. And the total number of dependent variables in the null space, number of independent variables in the null space rather, x2 through x2, x4, x5, and x6, these are independent variables is my point. Yeah.
So what you're saying is that in the, like the dependent variables will show up in the null space, right?
I would say here that I wrote the pivot columns corresponded to dependent variables in the solution set. Because I'm writing x1 in terms of everything else except for x3.
And then only the non-pivot columns will show up in that.
Yeah. So then you've got pivots plus non-pivots, that's everything, which is n. That's the rate nullity too. Yeah.
Okay, I'm sure this has probably been asked, but basically, x is an element of null space of A. That's all x, and that makes AX equal 0. And from what you have written there, it depends on like the number of pivot columns. Like you have 2 pivot columns, like this makes you have 2 dependent variables, and all the rest of the 4 of them use free variables.
Right. Yeah. And it's not just this example. I mean, this pattern we're observing generalizes to arbitrary matrices. So, but if you can understand this example, you pretty much understand the general case. That's why I did the example. This example is not quite nasty enough to see it. I should have picked a harder example to start, but it's probably good for you to see 2 examples anyway. Okay, so, I mean, the solution of AX equals to B, what is it? Let me describe it now that we have this. We have all the toys we need to describe the solution set. Now let me just get to it and do it. First of all, when is AX equals to B consistent? A in Rm by n, B an element of Rn, then AX equals to B is consistent. What's consistent mean? There is a solution. There is a solution, right? What condition do I need as it relates to the null space and the column space of A in order for there to be a solution?
Would the null space equal 0?
No,
Would nullity?
that's not it. It's the column space. Yeah,
Doesn't B have to be a linear combination of the column vectors of A?
exactly. So in plain language, B has to be an element of the column space of A, which is just a fancy way of saying what you just said. So if B is an element of the column space of A, it's consistent. Okay, point number 1. So given AX equals to B is consistent, all right, any solution is of the following form. And when I say solution, I'm of course referring to what equation? I'm talking about solutions to AX equals to B, okay? It's of the following form. X is equal to X, XP plus XH, where XP is a specific, sometimes called particular, solution, meaning that A times XP is equal to B, okay? And XH is equal to what?
Homogeneous solution.
Right, XH is, well, particularly it's an element of the null space of A. Yeah, and it's a homogeneous solution. Well, let me not clutter this here. Sorry, I wanted to say something greedier. Let me not do that. Where XH is equal to C1V1 plus C2V2 plus plus let's see here, C nu, V nu, where nu is equal to the nullity of A. And what? A times B I is equal to what? 0, right? Or I equals to 1, 2, da 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 da. Yeah. Yeah.
So is that like the differential equations, like model?
It's the same structure.
Is it also how you solve recurrence relations?
Yeah, there's something similar with recurrence relations, but I have less to say about that out there. So, you know, oh, I should be more clear too. You know, I'm thinking of the green forbidden.
Actually, it still exists in the null space.
Here, V1, V2, da da da, V new is basis for the null space of A. Right? I tried to collapse together a couple of theorems I had in section 6.7, so you should read 6.7. It's written a little bit more carefully than I'm trying to get the big idea across to you. I may have forgotten some little bit here or there today with this. So reading the notes, you know. The essential point is how do you prove this theorem? Let me show you the essential calculation here. So suppose you had two solutions, right? X is any solution, and XP is, you know, a particular solution, which doesn't have any significance except to say, really all I'm saying is I have two possibly distinct solutions to the equation AX equals to B. All right? So what you do then is consider, what do? You do A times X minus XP. What happens then? It's going to be equal to B minus B, 0. Exactly.
Right,
So, yeah, B minus B, which is equal to 0. And what's that say about the difference of X and XP?
Part of the null space.
Right? But we know we can build the null space as a span of those fundamental vectors, like we were just finding for that example. Right? Then the next step is the claim of the theorem X is equal to XP plus C1 B1 plus da 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 plus C new B new. There you go. So there are as many parameters, all right, in the general solution as there are vectors in the basis of the null space. Or in other words, you'll have a solution, an honest goodness solution set, which is infinite only when what happens? When you actually have non-pivot columns in the reduction of A. We already know this, right? But I'm just trying to recast all those things we learned before now in terms of the row space, the null space and the column space. Yeah. But yes, there is a very, very similar story which is told in differential equations. All right. In differential equations, but let me save that actually for a little bit later today. So I'm going to transition now and start talking to you about linear transformations for the remainder of class. So at least we're a little bit into today's actual lecture. So that's good. 15 minutes. Now we're only a half hour behind. Wait a minute, we go to 12:30, right?
Right. We can. No, like, the proposed rule I get out.
You're like, you can go to 12:30, but I won't be here. Yeah.
I mean,
So impatient.
I mean,
I have good news. What I'm about to tell you about is far simpler than what I've been doing. Like, this is kind of, I mean, this is technical a little bit. I mean, but this is the base of everything. I mean, more or less, given more other problems which look complicated, after we pick a basis and do some things, it almost always will boil back to these things at some more basic level. So it's, you know, we need to know these techniques. But, and I mean, row reduction's row reduction, right? It never really gets much easier. Because we never really escape the fact that we're not that good at arithmetic. Well, at least most of us. I used to be good at arithmetic. Then I grew up.
Would you rather be
Maybe
good
if
at what you
people,
are now?
maybe if people still offered me candy bars to do it fast, maybe I would be good at it again. I don't know. But then again,
Full-fledged
candy,
candy bars? How big
I
were
don't
those
really
things?
feel terribly great at candy bar though, so I don't know. Not really much of an incentive.
It's like there's like incentives to do arithmetic fast in elementary school still. I just don't remember what the prizes were.
Mad minutes. Do you guys do mad minutes?
Oh, yeah.
I think they were called like rapid fire problems in our class. We were timed to do like 30 problems.
Math is still a word we're allowed to use, right? Math hasn't become politically incorrect yet, has it?
Well,
I mean, 'cause in
Common
some
Core
sense-
kind of destroys it.
I mean, like a mad minute, aren't we kind of like making fun of mentally imbalanced people there?
I don't know.
Seems like it should be a forbidden term.
Or we're saying that they're skilled
Oh.
because they do it fast. The mad person could do it in.
Well, mad science is
so
also insane.
we're saying that crazy people are actually smarter than
I
us.
like this.
Insane people are smart.
My favorite thing about like those things was like competing against my fellow students and always winning and getting all 30 of those problems done.
Let's see your linear transformations. Guess what?
Didn't like that.
You're like, wait a minute, linear transformations, didn't we already do that?
No, we didn't.
We did in a specific context, okay? We talked about linear transformations from Rn to Rm. So I'm just gonna take it to another level today. We're gonna talk about linear transformations. So let V and W be vector spaces. We're keeping it real.
I don't know why that's so funny to draw these things.
I don't know, I'm thinking of writing a book. Be like, all the real things in math people don't care to talk about. It's true though, like certain questions you ask, like there's these people called representation theorists, and they refuse to work over the real numbers. Like, they're like, the complex numbers are beautiful, I will only do my results there. If you want to figure it out in the complex and the reals, you can go figure it out for yourself. It's beneath me.
Well, you said you wanted to write a
So
book.
annoying.
Well, I say, like Dr. Howard Towns would say, go ahead. Start the library right now.
T.
It wasn't that bad, was it?
No, I was just coughing. T from V to W is a linear transformation, provided what? Function such that what? One, additive. And two, homogeneous. Keep in mind that x and y are abstract vectors now, all right? If you have these two things, we say t is what? Linear transformation, all right? Or sometimes we'll say it's a linear mapping. I denote, so it's nice to have a name for the set of all these things. I'll say that T is actually an element of, sometimes script L, VW, sometimes I write it just regular L, but this is my notation, linear transformations from V to W. People who know better would write something like VW, but we don't write that because it's scary. Oops, I wrote it, sorry. Erase it from your memory.
He's allergic to scary.
Is that Tom?
Yeah,
Homogeneous?
homomorphism.
Oh.
Maybe that's not scary.
What is a homomorphism?
What is a homomorphism? Well, in our context, a homomorphism is a linear transformation. The reason it's a linear transformation is it preserves the structure of the vector space. So generically speaking, homomorphisms are structure-preserving maps. Whatever kind of structure you're looking at here, in a vector space, there's two things, right? Vector addition and scalar multiplication. Both of those things are preserved by a linear transformation. Okay, so the first obvious example of linear transformations is the ones we already talked about. right? All those ones that are induced from a matrix multiplication on our end, those are in fact still linear transformations in the more abstract sense, right? But you got other more fun things. Like for example, you could look at ddx, say going from say smooth functions to smooth functions, right? So is ddx of f plus g, what is it equal to? And ddx of f plus ddx of g, right? And you can pull a constant out too, right? So if you've got that, I mean, differentiation is a linear transformation function space. So, I mean, differential functions. Now, this notation is kind of a drag. So instead of saying ddx, usually when people are talking about these sorts of things, they'll use a big D for operator. Right? So you can do things like d squared. What would d squared be?
It's the second derivative.
Yeah, it's the second derivative. So it's ddx of ddx, and so forth and so on, right? So another example, let me be greedy. You could let t equal to, gee, I don't know, how about a constant, an, the nth derivative, plus an minus 1, the n minus 1th derivative, plus da da da, plus a2d squared, plus a1d, plus a, well, yeah, I think I can put an a zero there. So this again would be a linear transformation that takes in a function which is at least n times differentiable and gives you back another function. And the fact that this is linear follows from the fact that every one of the things that I'm adding together here is a linear transformation. We'll soon prove, not today, that the sum, maybe never, the sum of linear transformations is once more a linear transformation. The reason I might not prove it again for you is we already proved it in the case of Rn, and the proof is the same in the abstract case.
Can we see that in proof and like be valid?
Probably not.
Say yes, please.
Probably not.
Oh. But it's
Now,
good.
there's one thing here maybe I haven't talked about. Why is A naught a linear transformation? What does it mean, A naught there? A naught's a multiplication operator. So like A naught times F, this is kind of silly. It's just equal to the scalar multiple of A naught and F, right? So like this is just multiplication by the number A naught. So that's also linear for kind of silly reasons. Yeah.
Could you also put a d to the 0 power, or is that different than?
I don't usually write d to the 0 power, but you could think of it as being next to a to the 0, base of 0, I suppose. Right? Now, if you look at t of y equals to 0, right? If you have t of y equals to 0, let's say y1 equals to 0, and you have t of y2 equals to 0, since t is a linear transformation, if I have t of c1y1 plus c2y2, right? If t is a linear transformation, I'm telling you it is, believe me, you believe it. You have c1 t of y1 plus c2. It's because derivatives, second derivatives, third derivatives, these are all linear. So you have to get a linear thing, you still get a linear thing. So if I have that y1 and y2 are separately solutions of this equation involving derivatives, so it's a differential equation, then of course what? Yeah, that's 0, this is 0, it's equal to 0. So what I'm showing you is if you understand, and so, you know, before you see it written this way, usually in a differential equation class, you'll see it written something more like this. an yn plus an minus 1, yn minus 1 plus da 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 plus a2y prime prime plus a1y prime plus a naught times y equal to 0. This is the constant coefficient nth order homogeneous problem. And I've just showed you that the sum of solutions is once more a solution. The reason for that is because you can write the differential equation as a linear transformation acting on a function. Actually, if you really think about it, these things, an, through a sub 0, they don't just have to be numbers. They could just as well be functions. It doesn't really change anything. And that, folks, is the nth order linear ordinary differential equation, which we solved in 334. I won't say, I mean, I can't, it would be unreasonable for me to expect you to be able to solve that here, because the techniques for solving this equation are not linear algebra. That's differential equations. It's actually, I mean, I can tell you, I can rattle something off for you, like y prime prime minus y equals to 0. So, gee, I don't know. Obviously, y is equal to cos x, and y2 is equal to sin x. I mean, come on, differentiate those twice, and you get back to them again. So, of course, the differential equation is satisfied. There's your two solutions. They're linearly independent. So that's enough. That's the solution set in general. Linear combination of those, but I know that because I taught differential equations. It wouldn't be reasonable for here. So let me just. I should be saying other things right now. I'm sorry. I feel like you guys are getting me into this somehow.
If there's like a homework problem, it's like.
I blame Christian. Oh, so one important example. So all I was trying to get across to you guys at the moment was that one important example of linear transformations is the statement of a differential equation of nth order, a linear differential equation. All right. There are so many other examples, though. Some of them might be surprising. So here's another one. L of f equals the integral, say, from 0 to 1 of f of t dt. So here L would be a mapping, say, from continuous functions. Well, I don't need the whole reals. I could just say continuous functions on the closed interval from 0 to 1 to the reals. Right? You can easily check from properties of definite integrals that L of f plus L of g, I mean, I don't know, are we in differential equations right now? I mean, calculus is a prerequisite for this course. I think this is what it bounds. I mean, the larger problem is, like, I can't keep linear in the box. I mean, linear goes where it wants to. It's everywhere. I'm mostly, these examples, though, mostly are to give you a sense of how general this idea is. A lot of those things I said earlier this course, like you've seen this pattern of linearity other places, you can actually be more quantitative about that right now, right? Like differentiation is a linear transformation on functions. Definite integration is a linear transformation on functions. Indefinite integration, that's a little funnier because indefinite integrations does not give you a specific thing. You guys think about this? So here's an example that I need something else to figure out. What's the integral of f of x dx, right? It's equal to f of x plus c, where what? F prime of x is equal to f of x, right? That's indefinite integral. For example, the integral of x dx is equal to 1 fx squared plus c. But if people had more patience, what they should write here is not this. What people really should write is something like this. It's this set, 1/2 x squared plus c, such that c is a real number. Because honestly, the indefinite integral is not a function, it's a set of functions, which differ by some vertical shifting.
Don't we just assume that c is any real number?
I mean, you can make any kind of ad hoc assumption you want to about c, but the fact remains that the concept of the indefinite integral has to include all possible antiderivatives for a given length of a. My point to you is that's not a function, because it's multiply valued. So it's not a linear transformation, even though it has linearity.
Oh, okay.
Of a
That's why
sort.
you're doing that stuff.
This actually fails the function criteria. So I need something else to make that into an honest linear transformation. We will eventually recover that as an example, but I need something else. Be careful. All right, so next time I'm going to tell you all these wonderful theorems about linear transformations. Let me just rattle them off for you right now. Linear transformation of a linear combination is again a linear combination, that's right. If you have a linear dependent set, the image under linear transformation of a linearly dependent set is once more a linearly dependent set. The image of a linearly independent set is in fact a Haha, I tricked you. Not always true. It depends on the nature of linear transformation. So that's what we'll talk about next time.
Knew there was gonna be one.